welcome to Ushendra's engineering tutorials. Yet another important video from the playlist Measurements and Instrumentation. An important information which you might have skipped, which you might have neglected, or which you may not have been taught by your teachers. Right? So come here. It's something about a basic meter. It's a basic meter, a very important component which you have to know. Why? Because it plays a very major role in constructing ammeters, voltmeters, and even ohm meters intended to measure unknown resistances. Right? It has a very much importance in measurements and instrumentation. How the construction is: here we have like a north pole permanent magnet, north pole and south pole on either side like this one, and in the gap we have a coil suspended like this one. We have a coil wounded to this one like this. We have a coil like this, it's a coil, and when current passes through this one, and once another important information is this arrangement is suspended, like it's free to move, like it's a suspension. It's free to move like this on its axis. It's fixed over here and it's suspended like this one, right? So with this arrangement, when current, we have a pointer connected to this one, like a pointer connected to this one, and whenever current flows through this coil, whenever current flow enters and leaves through this coil, this current flow of current induces a magnetic field around this one, magnetic field over in this area, and even that induced magnetic field has poles, and the current entering, that will be the north pole here, and the current leaving, that will be the south pole, right? And more the amount of current, more the field strength, and more the repulsion, right? The repulsion. Now this, what happens is, we have it's a suspended, so more the amount of current, more the strength of the magnetic field, and so it starts repulsion. The repulsion starts. It cannot move away, it's fixed but suspended. It takes this rotation like this one, right? Now this meter will be, now we have an arrangement, we will be having a scale like this. Now this meter, like when no current, this position of the scale may be 0, it may be amperes, 0 amperes, and go on increase, the pointer starts deflecting like this one. It starts deflecting, and it may be 1 ampere. This will be the scale, right? So, and as soon as the current, it go on increase, the amount of current flowing through the coil is increasing, more the strength of the magnetic field and more the repulsion, and so the pointer takes more deflection. It may be 2 amperes, it may be 5 amperes over here, and it may be 10 amperes over here. This is the arrangement. And another statement to be underlined: when the current is removed, okay, when large amount of current, it may be 10 amperes flowing, the pointer is like this one. So after removing the current, what should happen to the pointer? It has to come back to its original previous 0 position, right? We have a spring arrangement, yeah, with a green one. We have a spring arrangement underneath this one. We have a spring arrangement like this. Now this takes care of that action. As soon as the current is removed from the meter, the pointer should come back to its 0 position, and this spring action, which we cannot see, like it's underneath, the arrangement is underneath, and this wounds and this brings the pointer back to its 0 position when we remove the current, right? And this pointer is made up of a metal, even the spring is made up of a metal, and even this wire, it's a spring is made up of a metal, and this coil is made up of a metal. So metal, it has some resistance, and that will be the internal resistance of the basic meter, a very, very important factor. Rm, they call Rm suffix m, meter resistance, right? It will while designing an ammeter, while designing voltmeters or ohm meters, ohm meters intended to measure resistance, we have to look back to this. This will be very helpful in designing the basic meter in different applications. Meter resistance, internal resistance of the basic meter. And this one, it's a permanent magnet and a moving coil, and so this arrangement is known as PMMC, permanent magnet moving coil. This arrangement. Now a basic meter as an ammeter. we have a 0 to 10 amperes ammeter. How to change the range of this one, how to extend the range of this one, how to change the scale of this one. 0 to 10 amperes, we have to make use of this one to measure 0 to 50 amperes, 0 to 100 amperes. How to change the scale of this one? From this arrangement, one important parameter has to be considered here. The maximum value showing is 10 amperes. In the sense, the maximum amount of current the basic meter can handle is a 10 amperes only. It doesn't carry beyond that one. If by forcefully, if we make current flowing through this basic meter being above this one, it undergoes throttling and the arrangement may get damaged. May not, it will be get damaged. So it's not suggested to measure beyond these values. And from here, the maximum amount of current the basic meter can handle is 10 amperes. That has got some importance in designing all these basic ammeters and voltmeters. It's a IFSD, the full scale deflection current. It's known as a full scale deflection current, IFSD. Full scale deflection current, IFSD, is the maximum amount of current the basic meter can handle. For the example being treated over here, in this case 0 amperes to 10 amperes, so the maximum amount of current the meter can handle is 10 amperes only, right? So what to do? This IFSD, in some textbook it's meter current IMI suffix M. So meter current in some other textbooks, one like this, and these two notations for the maximum amount of current the basic meter can handle. Now how this 0 to 10 amperes ammeter, how to change how to increase the range of this one is the question, is the objective, right? For example, considering an example, it may be extended to any range by following some precautions. But for example, let me tell you, like what if 0 to 10 amperes, we need to extend from 0 amperes to 50 amperes, right? But just now I've told you this is capable of handling only 10 amperes. We need to extend the range up to 50 amperes. For that, we need to introduce a shunt resistance like this one. Shunt resistance RSH, right? And we cannot place whatever value we want. We need to maintain some conditions. Then only it will satisfy our condition. Like 0 to 10 amperes can be extended to 0 to 50 amperes by maintaining some conditions, right? Whenever we'll start from the higher end, then go to the lower end for better understanding. For supposing 50 amperes is made to flow through this one, I'll place this resistance in such a way that when 50 ampere the maximum current is flowing, the maximum current that I'll make sure that I'll place a resistance over here which allows the maximum current of through the meter, the maximum amount of current it can handle, right? When 50 amperes, I'll make sure that I place a resistance so that IFSD flows through this resistance, through this basic meter. In this case, IFSD is 10 amperes, right? And 50 total, my total current I total is 50 amperes, and this, by placing this shunt resistance, I made sure that 10 amperes is flowing through this side, right? 50 amperes, right? 50 amperes corresponding 10 amperes will be flowing through this. The pointer will be indicating 10 amperes over here. I erase this one and I make sure that I'll overwrite it with a 50 amperes. This is what. And after this is done, what did I do now? I placed a shunt resistance, right? I made sure that while 50 amperes input is given, I made sure that the value of the shunt resistance makes 10 amperes of current flowing through this side. Why? Because according to network theory, definitely we can do that by having a control in this resistance. We can have a control on the current flowing through this loop and this loop. Like increase this resistance, increase the value of RSH, the current through this loop will be decreasing and that will be increasing. In the same way, decrease the shunt resistance, current through this loop will be decreasing, current through this loop will be increasing, right? So that's how we have a control on the currents flowing through this loop and this loop. For the time being, 50 is my total current, the highest range, and 10 amperes my pointer would be pointing to the 10 previous amperes, and now I erase that and make it a 10 amperes. Right? This is not all. Stay with me. The actual discussion starts from here. It is okay, but what to do with the next one? This is the point where you might have missed. Right here. So 50 amperes is the input, 10 amperes is the current through the basic meter. How much would it be flowing towards this one? 40 amperes, right? And what percent of 50 is 10? I guess it's 20%. In the sense, whatever current is flowing through this one, we don't touch this anymore now. After going with this arrangement, the maximum current and IFSD flowing through this side, we don't touch this resistance anymore, right? And with this arrangement, see this, 50, 10 is flowing that side and 40 is flowing towards this side. In the sense, 20% is flowing through this side and 80% is flowing through this side. Right? We are done with the 15. Now, what is the next level? I guess it's 40 amperes. I don't touch this RSH anymore. It's not a variable. I fixed it. And now for supposing now here, the total current is IT is 40 amperes now. 40 amperes. Right? I didn't touch this one, so there will what amount of current flows through this one? Right? Once the 50 is done, the highest range is done, we don't touch this anymore. This the current flow of current through this loop and this loop adjusts automatically with that arrangement. Now here, what is 20% of 40? I guess it's 8. Right? Check that one. 20% of 40 is 8. So my pointer would be indicating, my pointer position will be this. My pointer position will be this, and I'll erase this 8 and I'll make it as a 40 ampere. This is my new range. What about 30? 30 amperes, right? Once again, now we have 30 amperes flowing over here. 30 amperes. Once again, the same thing. What is 20% of 30? I guess it's 6. 6 amperes will be flowing over here, this side. 20% of 30. It's 6 amperes flowing this side. And left over 24 amperes will be flowing through this side. That's not, we focus on this one. And in this case, the pointer of the meter will be indicating this position. Right? And I'll erase this 6, which is the previous range. Now I'll mark this with 30 amperes. Right? So what about the next range being 20 amperes? The input is 20. Now the input current is 20 amperes. And I am not touching this resistance or nothing doing with that one. I've just reduced the range. Now, what is 20% of 20? It's 4, I guess. So my pointer would be indicating, this, my pointer position, this will be this, and I'll mark this as 20 amperes. Right? This is a new scale I am trying to design for. Right? So is that, what about this one? Make sure that the intermediate being 45 amperes. 45 amperes. Check that the 20% of 45 is 9. So when my input current is, my total current I total is 45 amperes, that 20% of 45 being 9 amperes will be flowing through this side, and the rest will be flowing. So when the current through the meter is 9 amperes, the pointer would be over this, and I'll mark it as 45 amperes. The same thing with 735, 20% of 35, that will be 7 amperes. I'll erase this 7, I'll mark it as a 35 amperes. So the same thing happens with all the values. 0 to 0. Right? So these have 0 to 10 amperes range. Ammeter is extended to 0 to 50 ampere by making use of a shunt resistance over here. The main important point over here is when the total highest current, I total is flowing, which is 50 in this case, 50 amperes, I'll have to make sure that though I'll have to select a value of shunt resistance in such a way that 50, when input is 50, I'll have to make sure that 10 amperes in this case, 10 amperes, which is the full scale deflection current, will be flowing through the basic meter. This is how 0 to 10 ampere ammeter range is extended to 0 to 50 amperes. Take it up. What to do? to have a multi-range. So for this may be for 0 to 50 amperes, one resistance RSH, shunt resistance RSH1. By having a switch arrangement over here, we'll have a switch arrangement S over here. This would be the arrangement. This may be for one range, another shunt resistance for another range, another shunt resistance for another range. In this way we have a multiple range, right? And the switch position, we change on the switch position like this one. This is for one range, this for another one, and this for another one. We have a switch arrangement over here, which comes in contact RSH2. This may be this RSH3. This is the third one, and the total current will be flowing over here, I total, right? And let me remind you, there is a disadvantage with this position, with this switch position. When the switch is over here, there is a disadvantage here. What the disadvantage is, watch carefully here. Let me suppose like the switch is in this position and the total current is flowing, right? And I need to extend the range, so I need to change the position of the switch from here to here or here to here. It may be during this transition. See, during this transition there isn't any, the shunt resistance is open during this 1 second of transition here. Okay, if it's over here, it's connected to this one, and okay, even if the transition is in microseconds time, but still in this transition from here, the shifting the switch position from here to here, during that transition there isn't any shunt resistance. The shunt resistance is open for that microsecond of time. During that time there is a chance of the highest current being passed through the basic meter and damaging the basic meter, right? So we need to have a protection. We need to have a range extension. At the same time, we need to have a measure for protection. So there is a small change in this arrangement. The shunt resistance aren't connected over here. There is a small change over here. We have a switch arrangement over here with S and a switch current switch connection over there, and we have a multiple here. This one, this may be another resistance, and so on. This will be this thing. I'll have a switch connection over this. This may be one of the connection. This will be another connection, and this will be another connection. The switch will be taking this position, and this position. When in between stage, it's completely isolated. Previously, it goes directly to the basic meter. In this arrangement, okay, like in between state, it's completely isolated. No current will be, the total current which is given over here doesn't pass through the basic meter. Now this is the important arrangement. It has got some name, guys. This one, how to pronunciate, you have your own pronunciation. It spells like this: shunt. This shunt, or else a universal shunt. It's known as a universal shunt for different values of RS. Now here RSH2, this will be RSH3, etc. This is the universal shunt. Please note. Now we cannot place whatever value of shunt resistance we want. That depends upon the circuit parameters, such as this. The current flowing, we'll have to make sure that the current flowing through the meter will be not less than IFSD, the maximum current flowing through the meter being IFSD. We'll have to place a shunt resistance maintaining this criterion, and the meter resistance RM being here, and this is my total current IT, right? IFSD, let me match this with my previous example. IFSD is 10 amperes over there, the first range, and this is the range to which, the new range to which the meter has to be extended. 50 amperes in my previous example, just now what I've told you, right? And this, the current, let the current passing through RSH be ISH, let it be. And it's very clear that I total will be equal to ISH plus IFSD, and we have no clue the value of this will be specified, and we have no clue on ISH. We don't have any idea, that won't be specified. So we have to express even ISH in terms of IT and IFSD. ISH will be equal to I total minus IFSD. This is the, now we have to substitute this one in some equation somewhere else, right? And this is in shunt with this one, so this voltage drop will be equal to this voltage drop according to potential divider rule. Writing that in an equation, what it is ISH into RSH is equal to this voltage drop IFSD into RM. What is this IFSD? Full scale deflection current. RM, meter resistance. ISH, current through the shunt resistance, and RSH, shunt resistance, which we are in search of. Now RSH will be equal to this one, IFSD into RM upon ISH. And we have no clue. We have no clue of this one, so that has to be replaced with IFSD as it is. SD as it is, RM upon ISH with this one, I total minus IFSD, and going ahead, IFSD RM upon IFSD into I total by IFSD minus 1. And something gets cancelled over here, this one, this and this gets cancelled, and finally what we have is RM upon M minus 1, where don't get confused, M nothing, M is equal to the total current, the new range of current, I total, the ratio, and IFSD, the existing full scale deflection current of the meter, IFSD. Right, I total is the new range to which the ammeter's range has to be extended, and this is the maximum range, existing maximum range. Now this is the this is the value for RSH. All these RM will be given, and this will be given, and even this is asked, even that will be asked. So this is my new value to be extended, so we have to place this much value of shunt resistance. An important expression which will be coming across, we'll have to make use of while designing a range extension of an ammeter. Make a note, please. Numerical for better understanding, a small design, range extension of an ammeter. It's given that the internal resistance of the basic meter is 75 ohm, being 75 ohm, this one RM, the internal resistance of the meter RM, 75 ohm, and the maximum amount of current the basic meter can handle, IFSD is 2 milliamperes. What should be the value of shunt resistance if the range of 2 milliamperes is to be extended to 10 milliamperes? 2 milliamperes should be extended to 10 milliamperes, and this 10 milliamperes will be our I total, right? And the question is, we are in search of this RSH. What should, from the previous expression, RSH is given as RM by M minus 1. It's RM straight away, it's 75 ohms, and M, this by this, it's 5 minus 1, it's 75 ohm by 4, which is equal to RSH will be equal to some 18.75 ohms. This is the shunt resistance that has to be placed across the basic meter if the range of 2 milliamperes is to be extended to 10 milliamperes. So basic information. Hope you find it useful, right? Please subscribe, share the content, and for more updates stay tuned to Ushendra's engineering tutorials. This is all for today's video. Thank you so much.